We actually talked about the concept of recurrent perturbations being generated, especially at mid-latitudes, because there is always the advection of potential vorticity substance into the westerly jet, and the westerly jet is unstable, so at the exit you are always having eddies that are propagating back towards the equator in the westerly duct and the upper tropospheric trough and so on. This is just a cute animation of CO2 from NASA. I'm showing that because it clearly shows that if you look at the animation here, you have constant eddies being churned even in the deep tropics. So if you want to relate convection to instabilities and convection is always there, then you need you need to show where that constant instability generation comes from, and that's the idea for looking at perpetual instability. Okay, you can. What did I do there? Do I have two of those? No. Okay, so we can look at that in terms of simple calculation again. So let's say inertial instability results from an imbalance between the environmental pressure gradient and the inertial terms in the equation of motion. So we can take a geostrophic basic state which has no zonal gradient but has a meridional gradient. So you have background basic state as a function of y, so there is meridional shear that is maintained by the meridional pressure gradient, and du dt, in that case the perturbation from the basic state, the balanced state, can be written just in terms of the Coriolis force on the meridional perturbation. So that v then is just dy dt. So then dv dt can be written in terms of f times u bar g minus u, where of course dv dt and then f is constant. You can do the calculation there in terms of dp dy and so on. Okay, so that's a fairly straightforward setup we are looking at, and we can expand u around y0 when it's perturbed by distance or displaced by distance delta y in terms of the basic state at that latitude, plus delta u, and delta u of course is f delta y from these equation. Then u bar g y is minus 1 over f rho dp dy, which can be written in terms of the Taylor series as u bar at y0 plus du bar g dy plus delta y. Let's ignore the higher order terms for now. So this is just u bar g plus du dy times v dt. So you are writing delta y as v dt because v is delta y delta t, right? And du bar g dy is just du dy because u bar g is at y0 constant. So dy is v dt. So dv dt in this case can be written as d squared delta y dt squared, and rearrange those terms as minus f times f minus du bar g dy times delta y, and define this as ma. So f times y minus u bar g. So then you can write this as dma dy. So it's a simple manipulation. You can follow that through. Basically, we are trying to again derive wave equation to look for instabilities, right? That's what we are usually doing, linearizing the system and looking for waveforms. So d squared delta y dt squared plus f del ma del y times delta y equals 0, where ma is fy minus du bar g just u bar g. Okay. Taking that equation, then you look for conditions where you get instabilities. So dma dy is going to determine whether you are going to have an oscillation or a decaying solution or a stable solution, right? So this three figures we will look at: schematic diagram of inertial instability near the equator, The situation is almost identical to that portrayed in 13.13 that we will see, 13.3. However, a fluid ring moving, so we are looking at two cylinders, the fluid ring moving closer to the axis of rotation. So as you go to higher latitudes, there we are looking at constant radius cylinders. Here, as you move away from the equator, because we are on a sphere, you are reducing the distance from the axis of rotation, obviously. Radius decreases. So this will follow a spherical path. If absolute angular momentum of the fluid decreases towards the poles, IA dma over dy is less than 0, then there will be inertial stability. Basically, you can think of it as planetary vorticity increasing, but you curl your fingers around this meridional shear and you get that relative vorticity is less than 0. So eta or f is less than 0. So we are looking for solutions which are stable, unstable, and so on. So sorry, this is inertial instability because zeta g is less than 0. So as we saw in the case of a cylinder, if angular momentum increases away from the radius, then it's stable. If it decreases, as it does in this case, then it is inertially unstable. So we get the batter mixing as we saw. Inertially neutral, so if there is no meridional shear, then the relative vorticity, geostrophic relative vorticity is 0. Eta over f is 0, so absolute vorticity is 0, and you have displacement that is stable. And if you have dma dy is greater than 0, then it is inertially stable. So if you displace it this way, eta over f is 0, so the parcel is going to be brought back to its original position, so there is no angular momentum inertially neutral state where there is no angular momentum. So that was this case. This is the stable case. Okay, so I hope that's clear. It's a very simple example. Maybe I didn't say it as clearly as I could, but just listen again and look at the equations and the figures, and you will understand it simply enough, or read the book as well.